In this chapter, we will look at various factors that affect the performance of our database application. The topics that we will be covering are the parameters of the create physical file and create logical file commands, database locks, the override database file command, journaling, and commitment control. Let us begin with the parameters of the create physical file command. The maintenance parameter is used to specify how DB2400 should maintain a keyed access path. It can have a value of immediate, rebuild, or delayed. When immediate maintenance is specified, DB2400 updates the access path whenever an insert, delete, or update operation is performed on the database. With rebuild maintenance, DB2400 creates the entire access path whenever a program opens the file. With delayed maintenance, DB2400 keeps track of the changes to the key field and updates the access path when the file is opened. The recover parameter can be used to specify when recovery should be done in case a system failure occurs while the access path is being changed. This parameter is valid only for files having immediate or delayed maintenance. This parameter can have one of the following values: *IPL, in which case the access path is to be billed during IPL. *after IPL, where the access path will be rebuilt after IPL. *no, in which case the access path will be rebuilt only after the file is next opened. If *rebuild is specified for the maintenance parameter, the access path is rebuilt only when the file is opened. The force access path parameter can be used to specify whether the access path and associated records should be written to the auxiliary storage whenever the access path is changed. This can help reduce the probability of damaging an access path in case of system failures. The size parameter is used to specify the number of records that can be placed in each member of the file, the additional number of records that can be automatically added to the member in each increment, and the maximum number of times the increment can be automatically applied. With the force-right ratio parameter, we can specify the number of inserted, deleted, or updated records that are to be processed before being written to the auxiliary storage. When this parameter is set to NO, the system decides when the records are to be written. The reuse deleted parameter specifies whether DB2400 should reuse the space created by deleted records. The allow update parameter specifies whether DB2400 should allow records in this file to be updated. Similarly, the allow deletion parameter specifies whether DB2400 should allow deletion of records from the file. Let us move on to the create logical file command. Most of the parameters on the create physical file command are also valid for the create logical file command. You have the maintenance, recover, force access path and force right ratio parameters. Click on any of these parameters that you would like to look at, and when you are finished, click on the Next Topic button to proceed. The maintenance parameter is used to specify how DB2400 should maintain a keyed access path. It can have a value of immediate, rebuild, or delayed. When immediate maintenance is specified, DB2400 updates the access path whenever an insert, delete, or update operation is performed on the database. With rebuild maintenance, DB2400 creates the entire access path whenever a program opens the file. With delayed maintenance, DB2400 keeps track of the changes to the key field and updates the access path when the file is opened. The recover parameter can be used to specify when recovery should be done in case a system failure occurs while the access path is being changed. This parameter is valid only for files having immediate or delayed maintenance. This parameter can have one of the following values: *IPL, in which case the access path is to be billed during IPL. *after IPL, where the access path will be rebuilt after IPL. *no, in which case the access path will be rebuilt only after the file is next opened. If *rebuild is specified for the maintenance parameter, the access path is rebuilt only when the file is opened. The force access path parameter can be used to specify whether the access path and associated records should be written to the auxiliary storage whenever the access path is changed. This can help reduce the probability of damaging an access path in case of system failures. With the force right ratio parameter, we can specify the number of inserted, deleted, or updated records that are to be processed before being written to the auxiliary storage. When this parameter is set to NO, the system decides when the records are to be written. To specify the next topic that we are going to look at is database locks. When multiple users are accessing the same object simultaneously, one job's operation could interfere with another's. For example, suppose you have a database that maintains sales information in a company. Every time a sale is made, the salesperson immediately enters the information into the system. The database file contains a record for every item that is sold by the company. One of the fields in the record is used to maintain a total count of the number of units sold of the particular item. Supposing two salespersons make a sale of the same item and are updating the information into the database. The sequence of events would be like this. Salesperson X reads the record for item ITM003. He then adds the quantity just sold to the total quantity sold field. Salesperson Y reads the same record for item ITM003 from the file. He also adds the quantity he sold to the total quantity field. Salesperson X writes the record back to the database file. Salesperson Y also writes the record back to the database file. As you can see, the total quantity sold field has been updated only with the sale made by salesperson Y and has totally missed out on the sale made by salesperson X. How do we prevent such errors from happening? What needs to be done here is that when one user reads a record in order to update it, other users should be prevented from accessing the record until the first user has written the updated record back to the file. This can be achieved through the use of database locks. DB2400 supports 5 different types of locks. They are exclusive, exclusive allow read, shared no update, shared for update, shared for read. When a job places an exclusive lock on an object, other objects will have no access at all to the object. With an exclusive allow read lock, the job that has placed the lock can read or update the object while other jobs can only read it. A shared for no update lock ensures that the job that placed the lock has read access to the object. The job may also be able to update the object provided no other job has a conflicting lock on the object. In this case, other jobs can have only read access to the object. A shared for update lock allows both the job that placed the lock as well as other jobs access to read as well as update the object. With a shared for read lock, the job that placed the lock can only read the object while other jobs may read or update it. Once a job places a lock on an object, the kind of locks that other jobs can place depends on the type of lock that already exists. Here is a table that gives you a listing of the valid locks that can be placed by a job on an object that has already been locked. We can specify locks at 2 different levels. One is an object lock and the other is the record lock. Object locks, when applied to database files, establish the kind of access that you can have to a database member. Record locks, on the other hand, specify the access method for a particular record within a physical file member. Let us now move on to file overrides. Consider this situation. We have an application program that uses the data in a physical file oldcast to generate certain reports. We have a new database file newcast that contains another set of data in the same format. We would like to run our application program with the newcast database. Normally, we would have to edit the application program so that all references to oldcast are replaced with newcast and then compile the application all over again. An alternative is to use a file override. It allows us to temporarily override one file with another so that all references to the original file will be replaced with the new file for as long as the override is in effect. We do this using the override database file command. Here, we specify the name of the original file oldcast in the file parameter and newcast in the toFile parameter. Now, when we run our application, all references to oldcast will be replaced with newcast. This override will remain in effect until it is deleted. We will come to that in a little while. Another use of the file override is to temporarily change the attributes of an open file. Whenever an application program opens a database file, it is always the first member in the file that is opened. The only way to access a different member is by using a file override. In the file parameter, we specify the name of the file to be accessed. In the member parameter, we specify which member in the file is to be opened. Consider another example. To position the file pointer at the last record in the file, we can set the position parameter in the override database file command. Let us now see what happens when multiple overrides are applied to the same file. Suppose we apply an override to file A with the position specified as *end. Then we specify another override to the same file A specifying maximum members parameter as 4. This causes the second override to replace the first override, and the first override no longer has any effect on file A. However, overrides behave differently when they are applied across different call levels. So let us now look at call levels. Suppose you start a program A from your job. Since program A is the first program called from your job, it is said to be at call level 1. If program A calls program B is at call level 2, and so on. Let us see what happens when overrides are applied at different levels. In program A, we specify an override to the file oldcast specifying position as *end, and then we call program B. When program B opens the file, the override causes the file pointer to be positioned at the last record in the file. In program B, we specify an override on the same file specifying maximum members as 4 and position as *start. We then call program C. Now when program C opens the file oldcast, maximum members will have a value of 4 from the current override, and position will have a value of *end from the previous override at call level 1. When an override is applied at a particular call level, it is merged with the existing overrides starting at the current call level and working back to the lowest call level. When we do not want current overrides to be merged with the earlier overrides, we can use the secure parameter which prevents overrides from being merged. For example, suppose in program A, we override the file oldcast with newcast and then call program B. In program B, we override a file sample with the file oldcast and call program C. Now whenever program C makes a reference to the file sample, it will actually be accessing the file newcast as the overrides have all been merged. But we want program C to use oldCust itself. To achieve this, on the override statement in program B, we specify the secure parameter with a value of *yes. Now the overrides will not get merged and program C will use oldCust. Let us look at some more parameters of the override database file command. We have the inhibit write parameter, which when set to yes, allows us to run programs that make changes to the database files without those changes actually being recorded to the database. The force write ratio parameter, which specifies the number of insert, delete or update operations that can be performed on a file before the records are written to the auxiliary storage. The number of records parameter is used to specify how many records are to be moved at a time to the auxiliary storage as a single block. The sequential only parameter can be used to restrict the file to sequential processing only. We can also specify the number of records in a block. The end of file delay parameter is used to specify the number of seconds that a program should wait when it encounters an end of file condition before attempting to retrieve a record again. The scope of an override is limited to the job from which it is specified and does not affect other jobs. An override is in effect until one of the following events occur. A delete override command is issued. Another override is specified at the same call level. A return is made to a calling program. A job is completed. To delete overrides, you use the delete override command. You can either delete the overrides applied on a particular file, or you can delete all the existing overrides with *all specified for the file parameter. The next topic covers database journaling. Sudden system failures may result in databases getting corrupted. One way of ensuring that the system failures will not destroy our entire database is to maintain frequent backups of the same. But these backups will only reflect the state of the database at the time of backup. Suppose you make some changes to the database and the system fail occurs. Your database gets corrupted. You can restore the data from the backup, but the changes to the database between the last backup and the system failure will not be available on the backup. With journaling, data can be recovered up to the last transaction that was executed before the failure occurred. Let us see how journaling works. Journaling involves two AS400 objects, a journal and a journal receiver. The journal maintains information about which files are being journaled and which journal receiver is being used to record the changes taking place to the database. The journal records all the changes in the journal receiver in the exact sequence in which the changes are made. Suppose two programs A and B simultaneously update the same physical file, The journal records the changes in the same order in which DB2-400 processes them. A single journal can be used for a group of files, in which case the journal will record the changes to all the files in the group. Each change that happens to a database file is recorded as a journal entry in the journal receiver. Each entry in the journal receiver contains the following information: a journal code, an entry type code, a sequence number, a date timestamp, job name, username, job number, program name, file name, library name, and relative record number. When a new record is added to the physical file or an existing record is updated, the journal entry will contain a copy of the changed record. This is called the after image of the record. You can also have a copy of the record before it was changed. This is called the before image record. Journal entries are always written to the auxiliary storage before the change is made to the database record. If a failure occurs, you can make use of the OS400 Journal Management Facility to restore the database. The sequence of operation would be as follows. First, the latest backup will have to be restored from the tape. Journal management will then go through the entries in the journal receiver, starting with the first entry after the save operation. Each entry contains a relative record number of the record that was accessed. In the case of an update operation, the record in the database will be replaced with the after image from the journal entry. In case of a new record being added, the after image of the record will be added to the file. When a record was deleted from the file, the record that is at the location indicated by the relative record number would be marked as deleted. Let us see how to start the journaling process. First, we create a journal receiver using the create journal receiver command. Next, we create the journal using the create journal command. Here we specify the name of the journal receiver that has to be attached to this journal. Then we begin journaling the physical files using the start journal physical file command. Here we specify the name of the files being journaled, the name of the journal receiver, and also whether we want only the after images or both the before and after images. The physical file, the journal, and the journal receiver should all be saved periodically. Now, in case of a system failure, we can use the OS400 Journal Management Facility to recover our data. To use journal management, we execute the work journal command and specify the journal we want to work with. The work journal command will take us through a series of menus that will prompt us for restoring the necessary objects with the restore objects command. We will also be prompted for the apply journaled changes command to recover the desired file member. When journaling is combined with commitment control, you get a powerful tool that facilitates automatic recovery. Let us see how commitment control works. Consider this example which we saw in the first chapter. A bank maintains customer information in a master file. It uses another database file for handling loans taken from the bank. Suppose a customer takes a loan from the bank. Every month, the bank will deduct the installment amount from his savings account and credit it against his loan account. This is done through an application program. Suppose the application program is running and it deducts the installment amount of rupees 5,000 from the customer's savings account. But suddenly the system shuts off due to a power failure. The installment amount has not been credited to the loan file as yet. This has caused an inconsistency in our database files. Commitment control is a technique that we can use to avoid such inconsistencies. It allows us to group a set of transactions together into a single unit of work. In case something does go wrong in between, the partial changes will automatically be removed from the files when the system is restarted. Let us see how commitment control works. First of all, we identify the files that are to be placed under commitment control. In our application program, we specify that the files are to be opened under commitment control. The commitment statement is used in the program to identify the commitment boundaries. The files that are opened under commitment control have to be journaled. We begin commitment control using the Start Commitment Control command. We can now run the application program. Remember to end commitment control when the application has completed. The first commitment cycle begins when the first database file under commitment control is opened. The changes to the database are recorded by the journal. The first commitment statement in the program marks the end of the first commitment cycle and the beginning of the next one. The changes to the data records are reflected to the database only after a commit statement is encountered. Suppose the system crashes in the middle of a commit cycle. When the system is started up again, it will automatically remove or roll back any uncommitted changes that are present in the journal. Both journaling and commitment control add additional overheads to the system and could affect performance. Hence, it is vital to plan carefully before proceeding with their implementation. Summary. In this chapter, we looked at a number of factors that influence the performance of our applications. We saw how various parameters on the create physical file and create logical file commands can be optimized to suit our requirements. Next, we saw how file locks and record locks can be set so that one user's application does not interfere or affect those of another. We saw how the override database command can be used to temporarily change the attributes of a database file. We also studied the journaling process. We saw how journaling and commitment control together give us a very powerful tool to perform automatic data recovery in the case of system failures.